But no matter how you swing it, your extraction device is going to become your bottleneck at that point. Like, even if you're not using a human to do all these samples, like you run into a bottleneck at some stage.
Welcome to another episode of the Omni Pod, where we're enabling conversations between life science thought leaders to help you get the most out of your preclinical research. Today, Caleb and Bill are talking about where microbiology workflows actually slow down and how faster bead-based lysis can keep your sample prep moving without sacrificing data quality.
I'm Bill Schick, Fractional CMO, and today I'm speaking with Caleb Proctor, Research and Applications Manager at Omni. All right, Caleb, welcome back. Good to see you.
Good to see you too, Bill.
In your experience, when diagnostic labs start scaling for testing, where do you typically see the bottlenecks in prep? Where do they appear first?
It was a really open-ended question because there's a lot of different pieces and parts that move around in some of these diagnostic labs. We have customers out there who work strictly from culture, and they'll take samples from things like urinary tract infections, and they'll culture all that out, and they'll have very pure or mostly pure cultures that they're then analyzing, right? And for a lot of the bottleneck there, if you take some of these traditional lysis steps and sample preparation techniques, you'll be taking, a sample that you run through a enzymatic or maybe a buffer-based lysis that'll get all this DNA and RNA, whatever molecule they're looking for, in suspension where they can then isolate it. But all that takes a lot of time. So some of this stuff you're talking about, with some samples like E. coli, it's pretty quick, right? And you have the benefit of having a cultured organism where the amount of cultured organism, even if you get a small amount of signal, is way more signal than you might need down the road, right? Like PCR is very effective at getting the detection you're looking for. So this may not be something that they want to have a bead beating step attached to, and they're getting great signal. It's not a problem. But there's some customers that'll have cultured organisms that they need. They're doing a rapid culture where they're trying to maybe do a few hours, and it's not necessarily a visible amount of culture there, but there's something grown, and they want to maximize the recovery of those analytes, right? So they introduce a bead beating step on top of that to increase the yield that they would get compared to other methods, right? And we've had some success in the past with, I won't name names on here or anything, but we've had some success in some of these labs because it speeds up their entire process, because this whole thing is based on a 96 well plate, so they can culture in a well plate, and then they can bead in that same well plate, and then move down into their extraction platform with all these various off-the-shelf kits. But what that does is it streamlines the whole process, and it keeps them from having to grow culture, isolate from the culture, put that in their super special lysis medium, wait a few hours. This is a few minutes, and then it's into a 30 or 40 minute DNA extraction and on to another 30 or 40 minute analysis. It really speeds up that time of detection. So it helps patient outcomes, right, on the back end. When these labs develop these workflows built around bead beating, it's very helpful. On the other side of this, there are labs that are trying to do detection directly from a sample, and this is more this is all R&D kind of work. But if a lab has a sample that comes in and there's a very low level of microbes sitting in there, instead of having to culture it, the holy grail would be immediate detection, right? Like where I worked at previously, that was always seen as like, here's where we're going. We want to have detection direct from a sample without culture and things like that. But to do that, you have to drive your assay to a level of detecting very low levels of microbes in a system. And on our end with sample prep, the way we can aid that is we can help these labs develop these workflows around lysing all their sample and getting all this, very small amount of nucleic acid out, and drive this greater detection. Because while in culture you don't necessarily need 100% lysis, you definitely need that if you're trying to direct detect something in a very small amount of tissue.
So a couple of different bottlenecks. You mentioned bead beating as a key piece of that and moving things along. What is it specifically, if you can paint the picture, what is it that makes that speed up the process of the workflow as opposed to maybe another mechanism?
Yeah, so the way I typically see these sample prep sort of setups for lysis is you'll have chemical lysis that's sort of initiated through like let's say detergent-based buffers, right? SDS, chaps, things like that. Ionic detergents that'll go in there. They'll just poke holes in the membranes of the bacteria. And then you have enzymatic-based digestions where you can put protease K, lysozymes. There's a few different enzymes that'll attack the actual membrane. And then you have physical lysis, which it could come in a lot of different ways. You could consider heat physical lysis. You could consider sonication physical lysis. But with bead beating, the physical lysis that we can provide with that is it's really fast. So back to what I said on the time, those enzyme reactions, they'll take for a full enzymatic digestion of some of these bacterial cell walls, depending on how thick they are, is hours. I mean, sometimes it's an hour. Sometimes you can get away with 30 minutes for some of these like gram-negative organisms. But these tougher gram-positive organisms, if you put them in a SDS and lysozyme mixture, well, the lysozyme kind of is hurt by the SDS. But if you're just using enzymes and it's sitting on a counter or in a heat block with a gram-positive organism, you may be looking at up to a day to fully lyse this, right? With our beads, wow. We can, and I could share this data. I'd love to put it in the show notes here, but we've seen with E. coli and various staph organisms, Staph aureus, Staph Epi, other streps, things like that. We've been able to get the lysis that we're looking to achieve to get this great detection in 3 minutes of bead beating, and then on top of that with like 2 minutes of dwell. So the bottleneck, you can imagine a scenario where a lab is going to have hundreds of samples in a backlog, and then as they're receiving them, we're talking about a quick 5-minute step here that feeds into these extraction pipelines. And on the other side of this, even if you could put all of these enzymatic and chemical lysis steps onto heat blocks and prep them, you still have this huge amount of time that you have to wait. And now the bottleneck is no longer that piece, but it's what is my extraction device doing, right? Like, it's easy to put stuff on a liquid handler and add all of these lysis buffers, add all these detergents. But no matter how you swing it, your extraction device is going to become your bottleneck at this point. Like, even if you're not using a human to do all these samples, like you run into a bottleneck at some stage. And on our end, it would just be like rapid lysis, move it into the extraction. When that extraction's over, rapid lysis, move it back into extraction, and it just quickly turns this into a beautiful workflow that helps aid in detection.
That's great. And I think that, for people listening, that probably makes sense, but they're probably thinking about doing some sort of automation and that being a significant investment. And as the counter to that argument, saying, well, listen, we can set up a handful of people to do all of this manually and save the money. Along those lines of thinking, what are some of the limitations, do you think, of some of the manual grinding or some of that prep that people they underestimate? They don't quite understand.
With bacteria in general, there's not a ton of manual methods to kind of point to on that, because it just, again, there's the liquid handling steps that go into that. The big piece of the manual side is I don't want to work in individual tubes, and I want to work in a well plate to kind of aid in this automated process, right? And seemingly, it's quick to move into these methods, right? When you want to go 1-to-1 with that. If you're talking about like an automated environment where you're working with something like tissues and things like that, that's where the manual grind and a grad student or a technician, their eyes just like kind of widen up and roll back in their head whenever someone's describing to them, hey, I need you to do 1,000 samples and you're using a mortar and pestle, right? I was once at a trade show where there was a grad student who had 30 mouse brains to work with, and she described her workflow where she was sonicating a mouse brain with a handheld sonicator, and it took 30 minutes to do this. Wow. And for each brain, right? And she had a project that had to be done, and I guess this was like in February when I was at this show, and it's like end of semester stuff because she wants to graduate on time and not be in school any longer than she has to be. And she was describing this as like, is there anything you can do to help do this? And I just point to the instrument to my side there, And I was like, we can do, 24 of those brains at one time here. And like, we could probably knock out this project in a day. And just like the immediate, like the relief that this person had for going from, oh, hey, I'm doing this one really old school, like sonication's old. It's as old as, I mean, I'm not going to say as old as you, Bill. I'm not, I don't want to call out anyone's age. Sonication's older than I am. So, there's methods that are built into these research papers, right? That people just keep referencing it time and time again. And it rolls into, a grad student that is using this ancient technology in terms of scientific advancement, right? Like there's there's much better modern techniques to do this work, and looking for very common analytes, just protein markers that they're looking for, and it was wonderful to help someone like that, right? Just pointing to one device and saying, here's how we can fix this problem. The other side of that is like some of these same labs have that, right? And they're looking at gaining back their researchers' times and turning these, now semi-automated workflows into deeper, fully automated walk away. I need my researcher back in the lab, like thinking about and solving and crunching the data. And that is a whole other aspect, right, where we can kind of approach it with walk-away automation.
I think you make a really good point there, and one of the questions it brings up for me is, let's say I have an approved workflow. My lab is set up. I already have all, my protocols set up, and I want to move from something that is a sonicator or more hands-on to an automated approach or workflow. What does that look like in practical terms for me? How difficult is it to take something that's in place, maybe with a sonicator, and just switch it over? Is it as hard as it seems?
It depends. It's one of those things where, in a research lab where you're able to quickly move from, one method to the next without having to go to your compliance department and ask, is this going to change the data? And then worry about the thousands of samples that you've created data around, and can you validate around that, right? It's a huge it depends question. And we struggle with that, right? There are people who have a lot of locked in methods that they need to have a one-to-one immediate fix for. And for those labs, a lot of it for me is just demonstrating the technology to them and show the value add to that piece, right? Like in the instance of this sonication, can we add value by saving your time, right? Like you're gaining 30 minutes in a single sample. Maybe that is the easiest way to convince somebody that they need to revalidate, right? So on one hand, you have the immediate, yes, I'm going to swap methods, and this is game changing, and I want to do this, and let's do it today kind of instances. But there are those complicated instances, right? Like we definitely have those labs that have a lot of requirements built around just changing willy-nilly, right? And it's good. It's good to have these regulations around that for just data and compliance issues, right? Like you want to be compliant, you want to have good QC on everything. So it does matter. But on the flip side, the good news is on our end, we do have some compelling work that we've done to show how easy it is to get reliable and repeatable data with these other methods, not necessarily in one-to-one scenarios, because as you know, in the scientific world, everyone's got their special snowflake, right? Everyone's got their special, here's my protein, here's my marker, and if you don't have my exact one, I don't believe you. Like I've lived that for a long time, so it's tough to nail every single thing down. But by showing a holistic, like here's some sweeping strokes where we show good compatibility, then we can dive into the nitty-gritty when it comes to the special snowflake situations.
Give me an example of that. Tell me a story about a special snowflake situation that.
Let's see. A good one would be there was a couple customers that worked with umbilical cord, and they had been working in one of these environments where they use scissors to chop things up, and they didn't have a perfect way to rapidly go from maybe one. They wanted to measure, right? Like they wanted to say, I need a way to measure this sample automatedly. And we know the story doesn't have a conclusion yet because we're still working on this. But I proposed the idea of you could use weight to to work around this piece, right? And it's a very novel way to think about it. But like all of these samples will have a range, and you can utilize weight, and then you, instead of utilizing a length to do that, because they're going to be pretty tight, and you can use automation to fix that with your buffers, right? So if you weigh them and you know how much this exact length weighed, then you add it. They always had a constant buffer, and my challenge to them was, maybe don't use a constant buffer, use a variable buffer to go with a variable weight that goes with it. So in theory, right, of course this is how this stuff goes, in theory, that could be a way to get what you're after. And it's kind of an outside of the box thinking, but on their end, their technicians were describing, having to have a ruler, and this is in a clinical environment, right? They're measuring the lengths of these umbilical cords, and they're cutting it to a very precise amount. And down the road, it was just like, we can use functionality on some of this automation to take away this pain, right? To give you the ability to put samples on deck, have a robot read everything, and then move into distribution of liquid assets on top of that, and then homogenization in a full-blown workflow. And they liked that idea. But again, that's where the compliance we ran into the roadblock with compliance, where it's like, oh, we got to revalidate, we got to know all this different stuff. And that to me, like I said, it's still got to play out. But that's one of the good ones where it's kind of a, hey, we have a good example of something that could work really well for you, but it's going to run into compliance. On some of the easier aspects, we've had some customers before who were doing it a grinding method, where they were grinding these samples in liquid nitrogen. They were worried about RNA loss, and they were using fresh samples that they would freeze in liquid nitrogen, which takes time and has cost to it, right? And then they would powder it, take the powdered sample, and then move the powdered sample to a liquid sample, and then move the liquid sampler onto an extraction device, like all these steps. And I proposed to them and said, why are we doing all this different work when we could just put these samples and your liquid in a tube and homogenize it in just a single step, like reduce three of these 4 steps. And they tried it, and they loved it. And it turned into, instead of having to use, a grinding jar, which can only use 2 samples at one time, it let them run 24 samples at one time, blew their throughput out of the water, and they were incredibly happy with it, right?
Wow.
But in that scenario, the compliance was only really looking for, is my RNA intact and able to go downstream? Because again, these methods are written that you must cryo grind, you must do all these different things. But if you can show functionality and then provide somebody with the value that's like, hey, this is going to save you a ton of time. Some of this stuff just takes care of itself, right? Like it's obvious to all parties, right, that this is a good fit. So that's the example of the easy ones, right? It's like we show them some very preliminary data on similar samples, and then they just run with it.
Thinking along those lines, sort of downstream, think about data reliability and making sure that in many cases, in every case, I need to be able to trust my data. But in some case, some of the sample prep process, homogenization, can actually reduce the amount of yield that you're looking for the process. Talk about that a little bit, and how all of this can have an impact one way or the other on your data downstream.
Yeah, so if you're talking about reducing yield as in like destroying analyte, is that, just to clarify, that's what you're talking about?
Yeah.
Yeah, so in some instances, you're going to have, this goes back to like, do you need to homogenize a sample or not? Some of these, like I said, kind of the first time we sat down and chatted, there's a lot of people who will use blood as a tissue, right, to extract valuable data from. And in most cases, I mean, you can pop blood cells by just adding water to it, right? You don't need a homogenizer for that. But in that same vein, if you have a tissue that's really fragile, you can pop those cells readily, right? Like let's just think about like a brain or something like that for a second. You can put that in our devices at low speeds with any bead media, and we'll lyse that brain. And then if you continue to run it, there's kind of I always draw this out on a whiteboard if there's a whiteboard nearby. maybe we can get editing to do this for me. But imagine like a graph, right? And you have percent lysis as it rises up, right? So you'll always get to 100% lysis. It's never going to be, you're never going to like gain cells, right? So it goes quickly up to 100 and flattens out. And then you're going to have the second line that comes up, and it's going to be the recovery of your analyte, which tracks with it'll track well with your percent lysis. But as time passes and you homogenize for longer, your analyte that you're after, especially if it's something as unstable as like RNA, right, will begin to degrade, and some of them degrade more readily than others. So it's really, really, really important if you have a sensitive analyte, and you as the researcher knows it's a sensitive analyte, it's paramount that you tailor make all of your homogenization settings around that analyte and that specific sample. You know, when I go back to special snowflake stuff, we always kind of build around good round numbers of tissues, right? But that's not hardly ever the case, right? Like many people will work with biopsies. People are going to work with whole organs, and everything in between, right? They'll have one grad student chopping up one piece, and if it matters, if your analyte degrades readily, maybe you standardize around a smaller piece or something that's going to that helps you get this repeatability that you're after, right? When the analyte doesn't degrade, you'll have a very consistent amount of recovery with a dialed-in method, and we've shown this before with some of our tissue samples that we've done. For example, we've done some skeletal muscle BCA work, and it's as close as I can get to a repeatable sample. It's really hard in the tissue world to find something that's a standardized sample, so I just use skeletal muscle from the same line of organisms. And we've shown intraday and day over day repeatability of these assays with really tight tolerances, as long as you're controlling for sample size and using the same exact protocol over and over again. But for example, like a BCA assay has like just if you put in standards on top of that assay, has like a 5% CV on top of it. Our homogenants, when you subject it to the same BCA, the CVs of these identical pieces of tissue running through a homogenization process and then having total proteins analyzed, only has 8% CVs. So like if you back out the CV of the assay, like these are nigh identical looks at the same pieces of tissue, which gives heavy confidence that these, methods are very repeatable, right? It just turns into understanding your analyte, right? I mean, long story coming full circle here, it comes back to like really just dialing everything in to specific targets that you're after. There's no one size fits all, unfortunately. I mean, I wouldn't have a job if there was. Like they would have had me for 6 months, and we could have nailed some stuff down, and then I'd be on my way. But luckily, it's that's the beauty of this job, is that everything's different and everything needs a special touch just to make sure that we're getting as much as we can out of these extractions.
Let's imagine we have a company that's moving, or an organization that's moving into automation. And they're, we talk about the LH96 for a moment here, away from whatever they're doing today and looking at an automation platform. What's some advice for them in the process of making that transition throughout the whole process?
Yeah, something like the LH is a big commitment. I mean, off the front end, like if you're going to get one of these devices, hopefully you have the throughput to justify it, right? Normally this device, just to back up, like most automation is purpose-driven automation, right? There's no Optimus robot coming in and like walking around your house and cleaning and doing this and all these different things, right? Like automation is laser focused on a single task. And when it comes to the LH, we try to do a lot of things to take the sample preparation off the hands of a user and put it on a robot. But when you do things like that, it adds some amount of time to these workflows compared to just a human just knocking things out, right? Like a human could sit down and be like, I added buffer, I added sample, I homogenized it with my little handheld homogenizer, and now I'm able to go downstream, lickety split, no times at all. The LH is not this like super fast, like what you would imagine, like race car driving, like throwing things on kind of automation. This is walk away automation, right? The idea is that you want to load samples on here, and then you want to press go, and then let a machine handle the work for you, right? So that you can go back to doom scrolling Reddit. Just kidding. But truly, it gives the user their time back. So the user would begin by putting samples on deck, and then the robot will pick up each individual sample. And maybe before you even came into work that day, you could have had the robot weigh all the tubes, and then you've loaded samples on there, and now the robot will move these tubes onto a scale, and it's going to get an accurate weight. It can dispense to the scale and get an accurate dilution according to that, so that you are not sitting there having to crunch numbers or plug things in Excel and make sure that you're weighing as accurately as possible, and doing all this while you're not caffeinated and ready to work that day. It removes a lot of that user variability outside of this, and then it can homogenize 8 at a time instead of using 1 at a time. But to do all this stuff, you when you're taking on an LH, like, you need to have a workflow that demands a throughput and a singular focused assay, where that you're not constantly having to change things, right? Like, you don't want to have to go through and validate 16 different pieces and parts for this. Like, you want to have 1 or 2 very robust applications that this thing can just tear through, right? And you'll have samples ready to go and move through. So it's not like this is something that every single lab in the world needs, right? Like, there are many labs that need some level of automation, but this is going to be a lab that's working with a lot of tissue in a very similar kind of assay.
You mentioned removing some of the user variability. Dig into that. What is some of the variability that you've seen?
Well, a lot of it it turns into with technicians. It's like, you hate to say it, but it's like some technicians are just better than others, right? When it comes to manual methods, especially with a rotor-stator, right? Some people are going to sit there and they're going to have the I guess maybe it would help. This is one of those times where the editor needs to come in, maybe flash a picture of an LH up. But you have a tube and then the device, and they're sitting here and they're like trying to chase around these samples inside the tube. And there may be users who don't do that as well as others, right? Where they'll turn it on, they'll do their thing, and it's like, okay, we kind of got a homogenant. And then maybe the next day they're well caffeinated, well stimulated, and it's Tuesday, and it's not no Monday scaries or anything like that. And the data becomes different, right? Maybe they ran it 30 seconds longer, and your analyte is more sensitive and it degrades. Those are the kind of user errors that we try to get rid of. Or let's say they're lazy at a scale, and you're saying, "Hey, I need 100 milligrams." I mean, this happens, man. Like, I've been in labs for a long time, and I've seen it. But like, you'll be at a scale, and your SOP demands plus or minus 1%, right? And let's say you're working with 100 milligrams of tissue. Well, 1% of 100 milligrams is 1 milligram. And you're at your scale and you're looking at this and it's like 102 milligrams. And you're like, close enough for government work. And you just slide that on into the next tube and you go on, right? Kind of thing. I've seen it. I've been a part of it myself. Like, it happens. Robot don't care. Robot will get it there, right? If the robot sees that it's 102, it'll add a little extra if you tell it to, right? If you tell the robot that you can handle these different dilutions this way, and the robot's not worried about having to change the pipetter, the robot's not worried about having to do different things, the robot's just going to do things, right? So that is where a lot of the consistency can come in when we talk about user error, right? And then the other parts of user error is you just get fatigue, right? So let's say you have 96 samples and maybe you don't have a variable pitch pipetter, or you don't have other fancy automation that can have these variable pitch platforms where you can pipette a bunch of tubes at one time and you're having to single channel move through all these things. That's a bear with 96 samples at one time. I mean, I've lived it, I've done it, and it's doable, but the LH can go through, move all these samples at one time into a well plate that's reformatted for an auto sampler or some kind of high throughput extraction. And that will aid these people at the end of the day. But yeah, removing the human from most steps almost always results in better consistency downstream. There's just too much, that we have as far as we can't see something happening. We're going differently in depth. There's so many different things that you can automate away inside a laboratory.
What are some recommendations for labs that are looking to make the change? So understanding that automation is, purpose driven. What are some recommendations then that you would have for a company that's starting to look at this and think about it in its workflow?
Yeah, I think a lot of it is like, make sure that your samples are all compatible with this kind of methodology, right? And some of that'll come through just discussion with someone like me who can kind of walk through some of your starting samples. We've had, and we do our best to kind of fit all these different, teeny tiny samples that come from small biopsies to humongous, organ pieces. But really understanding what it is that you're processing, and maybe if you can, to tailor that into a very common range of sample sizes. Because we have had some it's a challenge when they have, I'm trying to do this minuscule speck of a sample and an organ at the same time, right? And that isn't always compatible with each other. Sometimes it is. Sometimes it's totally fine. Like if you have imagine like a spleen from a mouse or something like that. It's a tiny, a half of one, a quarter of one, a tenth of one, and one spleen is like, it's the same piece of tissue. It doesn't. We're gonna hit that with the same probe. It doesn't matter. But in other scenarios, it's not the case. So really understanding what we can and can't do with single probes, and then deciding again if that throughput justifies it on the back end initially, and then on the flip side is deciding how many of these runs you're trying to do in one day, because at the end of the day, someone's still going to have to move something. Unless you've got some really fancy automation that has like robot arms moving things around that you're developing yourself, kind of thing. But queuing these things up and really dedicating your lab into an automated kind of facility, right? Like sometimes you can create automation that doesn't necessarily feed automation, and something like the LH may not be a great fit for that because you've got this big piece of automation for just your sample prep piece. And then you're still turning around in like maybe you're doing very low throughput analysis, and those don't marry well. So like you kind of want to make sure that your throughput is married together from top to bottom, right? There's just all these little pieces that have to come together to make just a holistic workflow that needs to be considered.
I mean, imagine for a second that you're talking to somebody who is considering, who's seriously considering this. Is there anything that you would want them to give a lot of thought to beyond what you've already mentioned? Or you'd want them to maybe know about the LH96?
So much of it really depends on what they're doing, Bill. Like, it starts with the need, obviously, right? Whereas like somebody says, I need this thing. And then you run into the aspect of, okay, well, is it a good fit? Right. And it really needs to be teased out. And that's why it's like when I was mentioning, like, we have these big chunks of tissue, like, are we working inside of a common range and things like that? Like, but for the most part, it's, just speaking plainly here, it's a very expensive item to kind of like throw in a lab. And most of these labs, where they balk at it is like, they'll see they have an LH that costs X $100,000, right? And then they turn around, it's like, well, my entire liquid handling and auto sampling setup that feeds all this other stuff I'm doing in the lab costs that much. And it's like, you got to get past that part, right? In my mind, it's like where you gain the most is getting back that sample prep time, right? Like that's kind of, if you're a lab that sees your technicians and your scientists spending so much time in sample preparation, that's where you can begin to see, especially with what we talked about earlier with these rotor-stator devices, if you see them using them and they're doing a lot of that work in a single channel mode by hand, it's like, this is probably a really good fit for an LH. Like we don't have to revalidate a lot of stuff. Like it's the same technology. It's driven by nearly the same motors. Like it's going to be doing all the same stuff that you're doing as a human. And let's get this time back, because at the end of the day, like we can recoup that cost with human use elsewhere, right?
Yeah, I think one of the key areas, so it's certainly an LH is, an investment. And if we just look at the dollars, sometimes it can feel hard to justify. But then if you look at sort of the bigger picture and reallocating that person, that technician that had to sit there and run a handheld all day long for how many days, weeks on end, and just rinse and repeat. Talk about that a little bit.
You imagine having a single user in this scenario, but I mean, there's even worse ones, right? There's three, four, five of these users in some cases that are using a handheld, and maybe you're the lab manager, the director of the lab, looking at that, and you're just seeing so much time spent in sample preparation, and a lot of the gain from the LH as an investment is not, it isn't going to be seen immediately when it comes to, oh well, we're adding a ton of value to this workflow in sensitivity. Like it may be identical sensitivity, right? But the value comes into the work that these people are able to do while there's a walkaway solution for the same exact work that they're already doing. So you can gain back, two or three of these workers to move to other projects. You have two or three other scientists analyzing data, thinking of new ideas to use in your lab and new workflows. And that's really where the LH kind of shines, right? Is gaining back all that time because you've taken away just these manual steps that one person's doing over and over and over again. And honestly, it's like sometimes this work just sucks. Sometimes like you just don't want to be sitting on a bench top all day, homogenizing things with a rotor-stator. And there's plenty of labs out there that have technicians doing that all the time, and it may be something that's a great fit there. So that would be my challenge: is if you see these rotor-stators getting used all the time in a high throughput manner with lots of people, this could be a great fit.
Yeah. Do you have an example that you could share with us? Obviously, keeping it confidential.
Yeah, some of the best examples are labs that went from like that 0 to 1 kind of mentality where it's like they were doing this at very small throughputs, and then just immediately were like, we need to do this and we need to do a lot of it. And then those are the ones we have the greatest success at. I don't, not off the top of my head do I have one where there's just like this huge need that has been built up over time. It almost always kind of turns into the people immediately saying, how do we scale this, right? Like it is a scale question, and not really this aha moment kind of thing. But I believe that there's more of the aha moment stuff that could come up if people knew it kind of existed, right? Like there's a lot of these tips out there being used in a lot of handheld devices, and there's labs that scale every day by just putting more man hours on it. And
Right.
it would do well to just know about this device and it could be changing for their whole lab.
All right, Caleb, thank you so much. You were great today.
Thank you, Bill.